Hello everyone. I'm sorry about not uploading videos on Saturday. I was too sick to be able to record these videos. Um, I'm again. What I will do is I'll postpone the online session to Friday to Thursday. So you have a couple of days for watching these videos. There will be only two videos this week. This one on associative forecasting, and the next one will be on error analysis, right? So let's get talking. Now, well, associative forecasting, as I discussed in class, is where you're trying to forecast the value of a demand or sales or something about a variable based upon the values of other variables. Now, the simplest way to do this, obviously, is using regression analysis. And here is an example of what we're going to do. So, Tire Rack, the company, they ask customers who use different types of tires whether they'd buy the tire again after using the tire for a while. So they gathered the ratings on a scale of 0 to 10 and they figured it out. And this is the rating that they got. That Goodyear, for Goodyear Assurance Triple Tread, it was 8.1 all the way to Dunlop SP20 FE. It was 3.3. Very people here are probably not going to buy that particular a tire, right? Now, at the same time, what they did was they took the tire and they had professional testers test it and give it a rating on steering and tread wear. So how does the tread wear, how quickly does it wear off, and then also steering, how well does it steer, right? So now the question is, if a new tire comes to market, right, and they're able to figure out the steering and tread wear, can they predict how if customers who buy this tire will buy it again, that the rating for buy again will be higher. So that's what they're trying to predict. They want tires that customers will come back and buy again and again, so that they can have it in stock, right? So that's the idea there. So how do we do that prediction? So we can run regression analysis on this, and we can go about that. So what I'll do in this video is I'll quickly go through regression analysis. There are a few important things about regression analysis, a few important questions to ask, and a few important questions that need to be answered. We'll go through that. Again, I'm sure you've done regression analysis multiple times, either at work or as part of some other course, but here it is again. So when you're doing regression analysis, things to remember is that there is always one. Let me open up a new Word file so I can write down some notes for you guys. So whenever you're doing regression analysis, you always have one dependent variable, and you can have multiple independent variables. So one dependent variable and multiple independent variables. Now the dependent variable is represented using y, and the independent variables are represented using x. So if you have multiple, you represent them as x1, x2, x3, and so on, right? And yeah, so that's basically it. And with regression analysis, the relationship that you're looking for is mostly linear. You can do nonlinear regression analysis also. It doesn't really matter. The way it works is very similar. So you'll end up with an equation that looks like y is equal to b0 plus b1 x1, b2 x2, b3 x3, and so on. So you're writing an equation where you're multiplying each of these variables with a coefficient, and all of that together will give you the value of y. Technically speaking, you don't get y, you actually get something called y hat. I don't really know how to put y hat here in Excel, so I'm just going to call it y hat. Right? It's y hat. So this is the predicted value of your dependent variable. So the value of this variable depends upon all of these variables. Now you won't be able to capture the value of y perfectly using any equation, because you cannot make predictions about any variable perfectly in real life. You can do a good job, but you can never do it perfectly, right? So b0 plus b1 x1. So this is a linear relationship where you're multiplying each variable with a constant. So you're multiplying x with a constant, each x with a particular constant, and you're adding them up. So if you have three variables, you have three of them. If you have two variables, you have two of them, and so on. But at the end of the day, remember that the values that we find out for these coefficients, the values that we find for these coefficients, they are average values, right? Because you have one sample of data here. For example, this is one sample of data for these 20 tires, for these 18 tires. You can take a different sample of 18 tires and run through the whole process again. You'll get a different data set where this linear relationship between the variables might be different. So that's something to keep in mind. So every time you take a sample, the value of the coefficients will change. So in fact, the value that you're trying to find out and the value that you'll find out when you run regression analysis on these variables is actually an average value. It's not the perfect value. That's why you can also find confidence intervals and all of that, because this is essentially an average value, right? Okay, so we're going to find this. We are going to find this equation. So you're going to find the coefficients b0, b1, b2, b3, and so on. So for in our case, there are only two independent variables: steering and tread wear. These are independent of whether a customer will buy something again depends upon steering and tread wear. At least that is what we are assuming. The question is, how well do just steering and tread wear impact a customer's decision again? And maybe eco-friendliness is something the customer is looking for. There are some tires that, and also say all-weather tires or winter tires or something. So depending upon the region that they're in. So there are other factors about tires that might be important for customers. But in this case, we are mainly looking for steering and tread wear to predict a buy again, right? Okay, I think I'm going to get rid of my face. I think this is making the video too large. Yeah, it's making the video too large. That's fine. I don't think that matters whether my face is there or not. Yeah, it's already too big. That's okay. That's no problem. All right. So let's run through the regression analysis, right? How do we? I'm so sorry. That's the wrong one. How do we come up with an equation that looks like that? So to come up with an equation that looks like that, we have our data, and it's actually very straightforward in Excel to do regression analysis. But a few things to keep in mind. So like I said, these values b0, b1, b2, and so on, they're all so let me formally put this on. So this value b0, b1, all of these numbers, b2, these are all random variables. They're all random variables because every time you take a sample, you're going to get a different value. So when you run regression analysis, the numbers that you get for these variables are actually average values, right? Okay, so with that in mind, let's run regression analysis and let's see what are the things that we need to keep track of, right? Okay, apparently I need to put a space in between that. Okay, so let's run regression analysis. Let me save this file. Okay. Now, running regression analysis in Excel is pretty straightforward. Just like you added, if you remember, you added solver tool. There is also a data analysis tool, right? So it's in a similar place. So if you have a Mac, you should click on tools on the top thing. You should click on tools. You'll get Excel add-ins, and one of the add-in is an analysis tool pack. You should check that, and you'll be okay. If you're on Windows, you click on file and you go through the same process that you did when you added solver. One of the other options that you have there is the data analysis tool, and it should show up here. Okay, so data analysis tools, you have all of these options. The one option here is regression. Now I'm going to use the regression tool here, but if you remember when we did the multiplicative decomposition method, we we found the slope and the intercept, right? So that is also regression analysis. You can in fact use the slope and intercept. You'll end up with the same value for b0, b1, b2 that we are going to get here, but this is a simpler method. This is much simpler in my opinion, and it gives you a lot more information. So I'm going to do regression analysis. Going to click on regression, click OK. Now the y values, so y values are by again, so this is our variable, that's our y variable. Now make sure that labels are checked, telling you that because I chose by again also, saying that the first value in the column is actually the name of the variable. And then of course the x value. So one of the things to keep in mind here is that if you have multiple columns with x, with a lot of x values and then y, make sure that all the x values are together, that there is no empty columns in between. So because you have to have a single range of all the x variables, all the independent variables. In this case, steering and tread wear are the independent variables. Again, what are we trying to do here? We are trying to predict whether customers are going to buy a particular tire again or not, based only on the steering and tread wear ratings. That's basically what we're doing here. All right. Once I have this, I want to get an output. So you can either get output in a new sheet, so it'll come up in a new sheet, or I'm just going to get the output right here. I don't want to get it on a new sheet. I'm going to say output should start, say, somewhere here, and then my output will show up right there, right? Residual plots, let's not do any of that for the time being, right? Click OK. So we get all of this information. I'm gonna, okay, maybe delete one column so it's yeah, so I can see everything. Good. So as you can see, so this is all the all the data that you got from the regression output. So there are of course very important numbers here, and we'll talk about that in a second, but most importantly, these are the coefficients that we're looking for, right? So with this, what this means is that if I go back here, the word file, so our equation was y hat is equal to so that was the y-intercept. So it says that's the y-intercept, and then you have the two coefficients, right? So think of this. So this is a straight line in three variables. So one variable is y, one variable is x1, the third variable is x2. So it's actually a straight line in 3 dimensions. That's the way to think about it, right? And so you have an intercept on the z-axis, I guess, instead of just x and y. You also have x, y, z, or y and x1 and x2. Those are the three axes. So y-intercept is a point where the straight line intercepts the y-axis, just like you have on a 2-dimensional plane. And then you have an equation for a 3-dimensional straight line. And what does the equation look like? So these are too many decimal places. I'm just going to keep two, maybe 4 of them, plus x1 plus x2. So what does this mean? So what are x1 and x2 here? So in our case, x1, so y is buy again, will customer buy again, right? And x1 is a tread wear, x2 is, I'm sorry, not x1, x2 is tread wear, and x1 is steering, right? So x1 is steering. So first variable is steering, second variable is tread wear. So we get this equation. So what is the use of getting this equation? So like any regression analysis equation, the use of getting this equation is that you can, well, make predictions about future things. So you can make a prediction about, let's say that there is a new tire that comes out and you know what the steering rating is and the tread wear rating, steering and tread wear ratings are, then you can use this equation to make a prediction on how likely is it that customers will buy that tire again. So that's what the main use of this equation is. And also you have the coefficients here. The coefficients also mean something, and so we'll talk about that in a second. But the most important thing is you can use this equation to use this equation to make predictions. Now remember, anything that comes out of this equation is a prediction. So in fact, what you can do is you can actually plug in these two numbers, say 8.9 and 8.5 into the equation. You are not going to get 8.1, right? So what exactly are you going to get? Well, let's figure that out, right? So and then we can talk about some of the other numbers here and here. So first things first. So predicted by again. Right? So first thing I can do is make prediction. So predicted by again based upon this equation. So again, so remember the equation of the line is right there. Y hat is negative 5.3876. So we have that number here, right? I'm going to make that an absolute reference plus the steering coefficient times the value of whatever steering you had. So times x1. So x1 is the value of the steering variable. Now this steering coefficient, again, I'm going to make that an absolute reference, but the value of steering, that itself is not an absolute reference. That cannot have dollar signs because that will change for each tire. But the coefficient remains the same. So coefficient remains the same, but the value will change. So I'm going to not make that an absolute reference. So with this, I'm writing this equation for Goodyear Assurance triple tread. And you'll notice that I get a rating. So I'm going to bring it down to 2 decimal places. I don't want so many. So the predicted buy again is 8.5, while the actual buy again was 8.1. So whenever you come up with these regression analysis equations, you're obviously not going to be able to be exactly on point. You're going to be around the ballpark, but not exactly on point. How good is your regression equation? How much predictive value does it have? That's what we'll talk about next. But first, let's actually make predictions for all the data that we have. There you go. So these are all the predictions. So for Michelin, the actual number was 8.3. We predicted 8.95. So some of these are higher, some of these are lower, right? So for example, Yokohama, the actual buy again was 8.9, but we predicted 7.88, right? So here it was 7.1, we predicted 7.08. We are very, very close. For some we are very close, some we are far away, some are above, some are low. But that's the predicted buy again value. Now, how well is our regression analysis line doing depends upon the difference between these two numbers. So we know the actual values of buy again because we actually went to customers to have them rate the buy again values. And now we know the predicted buy again values. So the difference tells us how good we are doing. So instead of just taking the difference, you take the difference and then you square the differences, you add them up, you do some average values and things like that. And that's residuals, right? And using these residuals, you'll be able to make a prediction of how well this regression analysis is doing, right? So how do I test if my regression analysis is working well or not? The very first number you should be looking at for that is multiple R squared. Before I do that, there's one other thing that we need to talk about. So you can use this equation to make predictions. So that's one thing. The second thing that you can use this equation for is the coefficients mean something. Say for example, the point 0.6899 is the coefficient. Or you know what? Let me just round that up to 0.69. Just 0.69. Okay. And 0.91. Let's just keep 2 decimal places. It's too, 4 of them is too much. So 0.69 is the coefficient for steering. So what does it mean? So remember, this is a linear equation. So what it means is that if the steering rating increases by 1, so if a steering rating for a tire increases by 1, while the tread wear rating stays the same, it increases the buy again rating. I shouldn't say it's a buy again rating by 0.69 units. So for every unit increase in steering, our buy again customer buy again, this rating increases by 0.69 units, right? Similarly, the coefficient for tread wear is 0.91. So if the tread wear rating increases by 1, so if you're able to increase the tread wear rating by 1 while the steering rating stays the same, shouldn't say it, buy again rating increases so if tread wear rating increases by 1 while the steering rating stays the same, buy again rating increases by 0.91 units. So what it means is that if you're able to get better tread wear on your tire, it is more likely to have your customers buy it again, right? So because 1 unit increase in steering has increases your customers' willingness to buy again, but not as much as say the tread wear rating. So this sort of linear relationship exists, and so that's what the coefficients mean, right? So these are all the things that you can get out of a regression equation. You know what the coefficients are, and you know what the coefficients mean, and you can use the equation to make predictions. But now the question comes back to us is, how good is this equation? Right? So to answer these questions, we can look at a few things. One, we can look at R squared. So R squared again, R squared measures how much of the variation in the y variable is captured by these x variables. Okay, so that's what r square measures. So let's look at the value of r square. So you'll see many r square here. It's the multiple r square that you should be looking at. I'm sorry, it's the multiple r square that you should be looking at, 0.96, not the regular r square value. The reason we should look at multiple r square is because we have multiple variables here. So multiple r square is what you should be looking at. And multiple r square is 0.96. No, I'm sorry, it is r square that you should be looking at, not multiple r square. I'm sorry. I usually use a different software. It doesn't throw up a multiple r square. Right, so r square is 0.93. What it means is that the variation in buy again. So you have variation in buy again. So the values of buy again are different for different variable for different tires. Similarly, the values of steering and values of tread wear are also different for all the different tires. You're saying that 93% of variation in buy again is captured by knowing the values of these two variables, steering and tread wear. So for a particular tire, if I know the value of steering and I know the value of tread wear, I can predict the value of buy again that I predict captures 93% of the variation of buy again. Now, this means that there is 7% of variation in buy again, around 7%, because this is around 93%, around 7% of variation in buy again has not been captured by this model, by these two x variables. What does it mean? It means that there is probably another variable that you can add to get the value of r square higher. So if you add more variables, r square values will increase because you're capturing more of the variation in your dependent variable. Or sometimes it's just random variation, right? So you have random variation, you can never capture random variation. In fact, a 93% r square is very, very high. I mean, this is obviously an artificial problem. In real life, when I do research, if I am able to get 60%, maybe even 65% r square, I am happy. I'm over the moon, because that itself means that I'm on the right track, and I'm working well. So the most important reason to keep in mind is that when you get a value of r square, it will be a number between 0 and 1, right? And the higher the value of r squared, the more accurate a particular model is. You cannot call it accuracy directly. You're just capturing the variation in the y variable, right? And that's basically what r square is. So r square tells you how much of the variation in the y variable, in this case, customer's willingness to buy again, is captured by these x variables, steering and tread wear. So in this case, 93% of the variation in the y variable is captured by these x variables, right? So which means that you have a really good model. You have a really, really good model. As long as you know steering and tread wear, you'll be able to make a very, very accurate prediction of whether the customer will buy the video again. The customer will buy the tire again or not, right? So that's one thing. And the other thing that you can do is you can run some statistical tests, but I don't think that's you know what, let's do one statistical test. So the second thing that you can do is look at is the model significant? Now, sometimes you might, let's say, get a r square of 0.5, right? Or you might get an r square of, say, 0.3. Question is, should we even be using this model at all? So if r square is only 0.3, which means that you're only predicting about 30% of the variation in y, should we be even considering these x variables? Maybe we should be looking at brand new x variables, or maybe or a completely different type of model, right? How do I figure that out? So for that, you have to look at model significance, right? So usually, if the values of r square are anywhere 0.5 or more, you are usually you're okay. You have a decent enough model for you to make small scale predictions. The higher the value of r squared, the better. And you increase the value of r squared by adding more variables, more relevant variables. If you add irrelevant variables, it will increase the value of r squared, but not by much. It'll increase it by 0.1% or 0.01% or something like that, in which case you know that those new variables are not that useful, right? Question is this model significant? How do I figure out if this model is significant or not? And we know that this model is significant because the r square value is pretty high. So the way you figure out if your model is significant or not is to look at this significance f number. So this significance f number here, I'm going to copy that. I'm going to paste that here. Significance f, the value of significance f is, So remember, whenever Excel throws up really, really small numbers, that is what it does. E minus 9 means 10 to the power of minus 9. So this number is actually 0.1, 2, 3, 4, 5, 6, 7, 8, 1, 1799, right? 179936. So there are 8 zeros in front of this. So you're moving the decimal places 9 times to the left. So it's a really, really small number. So the significance of the smaller, it should be a really, really small number. If it's a small number, it means that our model is significant. And how do we decide how small it is? It has to be less than 0.05 or less than 5%. So you get 0.05, right? So as long as the significance f number is less than 0.05, you can say that the model is significant. So if this number is more than 0.05, then you cannot say that the model is significant. Okay. So this is for the whole model. Should we be using this model at all? Now, similarly, you can also look at individual variables to see, let's say that you have 20 variables and you're predicting a particular y variable. The question is, are all 20 variables useful, or only some of them useful, right? So that's the other thing that you have to figure out. So you not only have to look at model significance, you also have to look at significance of individual variables. I'm not spelling significance wrong all the time. Wait, is this wrong? Significance. Why was second I right? Significance. So a significance of individual variables. So this is where you are going to run a test to see whether a particular variable is significant or not. And for that, you come back to this table right here, and the numbers that you check are the p-value numbers right here. So the significance value for steering is 0.029, and the significance value for treadwear is 0.0005. Now, both of these numbers are less than 0.05, so both of these variables are in fact significant, right? So for steering, p-value the p-value 0.02987, which is less than 0.05. So the variable is significant for treadwear. P-value which is less than 0.05, right? It's 3.005, yep, just less than 0.05. So this implies that the variable is significant. It's as simple as that. So to figure out if our model and our variables are significant, you just need to look at the p-value. So the significance of the whole model, that is in the ANOVA table, analysis of variance table. If this number is less than 0.05, then your whole model is significant. Otherwise, you don't need to use this model at all. You throw out the variables that you have and you start with brand new variables. Now for individual variables, you look at these p-values. Again, don't worry about the intercept. You always use the intercept that you have. With the individual variables, again, you look at the p-values. As long as they're less than 0.05, you're good. You should keep those variables as part of your model. Sometimes you might get R-square values that are, let's say, 30%, 35%. But when you run the model, the p-values for individual variables might be high, which means that the variables that you have are important variables, but you don't have enough variables to make a good prediction with the model, right? So there are multiple ways this thing can work. So keep that in mind. So this is for the whole model, and these are for the individual variables. And that's it. So that's regression analysis. That is everything that you can do with regression analysis. First is the equation. You can use the equation to make predictions, and you can interpret the values of the coefficients, which tells you something about the variables, something about how the y variable depends upon the x variables. And then the question is this a good equation at all? So there are three things that you can do to look at this. First is look at the r square value. It tells you how much of the variation in the y variable is captured by the x variables. And then you look at the model significance and the significance of individual variables. And that is regression analysis, and this is the best way to do associative forecasting, right? Okay, so I'm going to end this video here, and I'll see you all in the next one. Right? Take care.